in this loop. And in the upper boundary condition, we were not catching index 0 in the loop, which is the left side. So we are missing the upper left corner, and we have to calculate that explicitly here by making 2 ghost points, C at the top, and if we use a Robin boundary condition, it will actually be equal to this. And here we see that we are, this is discretization across the Z dimension, but at the very left side at position 0 in R dimension. Similarly, the left boundary ghost node will look like this, because C at I minus 1, which is the ghost point, must be equal to this first point right to the boundary in order for the Neumann condition to be equal to 0. So we will now put these into the two diffusion terms for the Z and R dimension. Here we are discretizing across the Z dimension, and we are substituting with the ghost point here. And similarly for the radial dimension, here we will substitute the ghost point. And we can now put everything together. And remember that DC dr was equal to 0, so we ignore that in the governing equation here. So this handles the upper left corner. Just add it here. So now we need to handle the fourth boundary condition, which is on the right side, or the wall, where we have the biofilm. So this will be a Robin boundary condition also, where we have the flux is balanced by the reaction at the very surface. So we can use Fick's law again for that. And say that it is equal to a first order rate, reaction rate. And here I write R, we could write NJ instead. Okay, and we discretize the CDR and then we get the following equation. That would be, whoops, mm, we would get this, and we then need to isolate this point, which is the ghost point, and like before, we need to do it in a for loop uh, over all the nodes on the set dimension. So we will make a for loop, and again we define the ghost point first, and that comes from isolating this one. If we do this, we will get the following equation. We can call it C right, and here I put in I for the index on the set dimension. Now, like before, we will calculate the different terms first in the set dimension, and nothing special happens in the set dimension here. It is just the discretized form of the second derivative, which I will copy paste directly in here. Oops, that was the wrong one. And then you just saw the D2C R2, which will come here. So again, we see the pattern with nj minus 1, nj in the middle, and then we have nj plus 1, which is a ghost point, and we substitute it in. So this, it's actually this expression going in here. And then we need CDR, where we also need to substitute, because that is nj plus 1, nj minus 1, divided by 2 times dr. And this one is a ghost point, C right, we will substitute here. And we can now calculate the governing equation for the right boundary. I will copy paste the equation here. So here we have a case where the radius is used, the position, and we will use our R grid and take the njth position and get the radial length from that directly here. And before we didn't have this term because it was 0 here, so it cancelled out and was ignored. But now we have to calculate it. That was the last boundary condition, but we are still missing the upper right corner now. And we can define that with 2 ghost points, like for the upper left boundary. That would be, when we have isolated it, it would be like this. for the right part of the upper right boundary, and for the top. So this would still be on the upper right corner, but the ghost point in the Z dimension, C top we call it. And we will define the different terms again. So this is central difference at the corner, where we discretize along the I dimension, no, the Z dimension. Good. And for the radial diffusion term, it will look like this. So here you just see discretization across the radial dimension. So that is nj minus 1 and so on. And then we replace we substitute with the ghost point. And for dc dr, it will look like this. We can plug this all into the governing equation for the upper right boundary. And we can take the code actually from this loop up here and use that directly. So now we have fixed the 4 boundary sides and the 2 upper corners. We don't have to fix the 2 lower corners because they were already included in the Dirichlet boundary condition, because to start with we said that all in the bottom layer should be 1000, including the corners. So we have now come to the interior loop, and in this case we will have to make a nested for loop. So we will loop over first. In the outer loop we will go through each radial position, that is the R dimension, starting from 1 and ending at nj exclusive, and that is because we already handled index 0 and index nj in the boundaries. Inside each loop on the radial position we will loop through the Z dimension. So we have the inner loop here. I will give myself some space here. And we will now code directly the different terms in the governing equation. Start with Z. So because the Z dimension, that belongs to the I indexing, so we discretize across the I in I here. Okay. And for the radial diffusion, we fix I and we vary J instead. And then we need the CDR. So we still have to vary along J here because the CDR belongs to the diffusion in the radial dimension. And we can plug it all into the governing equation, all the interior points. Like this. And we are almost done. Finally, now we have filled out all the derivatives, the time derivatives, but we have done so in a two-dimensional array, and this function has to return a one-dimensional array for the solve IVP function. So we have to now, again, we have to flatten the derivatives to the array to 1D array. And like we did for the initial conditions outside the rates function, we will use the flatten function for that. Sorry, the flatten method. Okay. And then we will try to solve the problem. We will simulate this for 1 day in seconds. And we will have the t-span here starting at 0 going to t max. And the initial conditions, that will be the C0 flat that we defined all the way up here. We will use the method of soda, and let's say we want it evaluated at 100 points. So we use, oops, use the NP lin space for that. And finally, we need to pass all the arguments that we need. And here we actually have to go through this whole function, rates function, and see what is defined and what's not defined. Here there is a bug somewhere. Like this, I think. Nope. Yeah, good. I will just put directly in all the arguments that we need from a script I already did. So these are all used inside this function. Okay. Missing an equal sign. Something is wrong here. We do not need these. These will always be passed automatically. And now we will run the code. See if that works. So since it's a 2D problem, it will have to solve a lot of ODEs, and therefore it also takes longer time to find a solution. But now we finally have it. And we can just see how the results look. Right. So we will have on the column axis here, we will have the different times. So we should have 100 time points here. And then when we go down along the rows, we have the position in the Z dimension. And then you get a new block coming here. So that is time again and the Z dimension, but in the next radial position. And we now have to make sense of this 2D array because we have 3 dimensions, time, R, and Z. And we need to plot this in a meaningful way. And we can do this by making a color animation where we let the color correspond to the concentration of hydrogen sulfide. And then this animation will change color over time in a 2D space. And I have used the AI to tell me how to make this animation based on how the solution output looks. And I have just copy pasted it here, and you can use this in your own code and modify it. Let's see how it looks. Good. So here in the bottom we see that a concentration of 1000 ppm, and in here we have the center of the tank, and we then have diffusion towards the top of the tank. And because we have a biofilm on the right side here, we have consumption of the hydrogen sulfide, and we therefore see low concentrations on the right side and higher concentrations on the left side. So this is more or less also what we expected. And I will conclude the video.